Oh, thank you for having me. And in an earlier incarnation, the last time around, when I was a young mother ham and still active in the club, I was actually listening to a HollyNet that caused me to ask somebody at Radio Shack about this, and then this gentleman put me in touch with Tony Young, WA3YLO, and then the rest is history, and I got into radio and the club, and I gave a talk way back when on, I was still at Goddard Space Flight Center, and I was talking about, I believe it was on Saturn and Titan, and things had changed a lot, and after that I went back to grad school, and the babies got bigger, and life took over, and so then in the past year I've been getting back into radio and getting back into the club, and still not enough time for it, but I'm trying to make it, and I just really appreciate the way everybody's welcoming me back, and so, and I find there's a lot of people like that where they fall out of it for a while. Kept my license current and everything, but just finding the time, and so trying to find that time. I'm still a dinosaur. I don't know the new modes. I mean, for me, it's either the repeater or 40-meter CW, and I gotta maybe start expand. Okay. Don't let me fool you, I'm not fast, and so but I did get my extra back when you had to pass the 20, and it took me 2 tries here in this room to do that. So anyway, I'm pleased to be here. And so back in 2011, I went down to NASA headquarters on detail, and then never ended up coming back. And over the years there, I've managed some different science programs, grants programs. I was a program scientist for the MAVEN mission at Mars, and other things, and then somehow a few years back I got sucked into NASA's growing, what was the Near-Earth Object Observations Program, and then what became the Planetary Defense Program, and that is actually a thing, and it sounds like something out of the movies, but it is a real thing, and so I'm pleased to get to tell you about it here. So, too many slides, but I'm going to do my best to plow through, and feel free to just jump in with questions, because I'd rather talk about stuff, and then I can always pare down what's at the end if as I go through the fire hose here. And the emblem there, there's stickers for it in the back too, and also some brochures on what we do, and on part of what we're involved with the UN. I don't know if any of that's still left there, but the sticker itself, if you're a Star Trek fan, and you've heard of Michael Okuda, he's the graphic designer for on the Star Trek series. He designed that for us because one of our people is a friend of his. So, in fact, I just shipped another pack of stickers out to him because that's the least we could do. He's designed a number of emblems for International Space Station and other missions, and so we're very pleased to have this. Okay, so maybe just a little 101, this terminology. So in space, if it's, this is something the International Astronomical Union has come up with. If it's larger than a meter in size, it's an asteroid. And if it's smaller than a meter in size, then it's a meteoroid. Some of us probably would have chosen a larger boundary, but that's what it is. So it's an asteroid when it's in space. When it's in the atmosphere, the meteor is actually the phenomenon, the visible phenomenon of it burning up in the atmosphere. And so that's the meteor. And then if it reaches the ground, then that's the meteorite. Just that terminology. And so the idea of, so what is near-Earth asteroids? You have asteroids out in the asteroid belt out beyond the orbit of Mars. But the near-Earth asteroids, it's defined as asteroids or near-Earth objects, or asteroids or comets, with orbits that bring them within about 1 1/3 times the distance from the Sun to the Earth, or 1.3 astronomical units. So that blue zone there represents the area that if an asteroid comes into that area, it might not spend all the time there, but comes into that area, it's a near-Earth asteroid. The thing is, a lot of the near-Earth asteroids, even though they come into Earth's neighborhood, never actually even come near to Earth, thank goodness. But there are, what we really want to keep an eye on are the potentially hazardous asteroids, the ones with orbits that bring them within 4.7 million miles or 7.5 million kilometers of Earth's orbit, that red zone there around Earth's orbit. So, and Earth might not be there at the same time, but just if an asteroid or comet comes within that red zone, then we keep that on a special list of potentially hazardous asteroids. We want to really watch where they're going to be in the future and make sure that that we and the asteroid are not in the same place at the same time. And if it's going to be, then do something about it. The other thing for a potentially hazardous asteroid, we get hit with stuff all the time. You see shooting stars, dust entering the atmosphere, burning up, sometimes larger fireballs, bright things, but our metric for something that's potentially hazardous, something that should it impact could affect a regional scale, like a state or a European country-sized area, 140 meters in size and larger. So we want to look for all of them, but those are the ones we really want to look out for. Okay, so we have the Planetary Defense Coordination Office, which does sound like something out of a movie, but even though NASA has had its Near-Earth Object Program since 1998, in 2016, the Planetary Defense Coordination Office was established at NASA headquarters here in DC to coordinate the planetary defense activities across NASA and coordinate with other U.S. agencies and with our international partners to address and plan the response to an asteroid impact hazard. And so in our mission statement, it involves detecting any potential for significant impact of planet Earth by natural objects. So we get a lot of, is it Space Force? No, they're dealing with artificial objects. We're dealing with the natural objects. Appraise the range of potential effects by a possible impact, and then develop the strategies to mitigate impact effects on human welfare. And so some things, as I said, are nice we don't have to worry about. This was a case back in a little over a year ago where a nice big bright fireball came in over Michigan, and it was an asteroid about 2 meters in size, so it wasn't that large. But when something like that happens over a densely populated area, it's a big deal because a lot of people see it, and so that happened, and the meteorites that came from that very small asteroid burning up and breaking up were spread over a strewn path, their strewn field. But based on how that meteor came in, could track it back to the orbit that it was probably following before it impacted Earth. But the nice thing was being able to recover meteorites. And in fact, it was nice because it was wintertime. They could go out on the frozen lakes, and it's a lot easier to find them if they're in the, rather than being like in the dirt and the trees and everything. And also for those of you who I know there's a lot of folks into weather here and Skywarn or weather hobbies or weather as a profession. One neat thing that's being used lately is to actually see meteorites coming in on weather radar. Be able to pick that up, and it's a very faint signal, but if you know something's happened, like with that Michigan meteor where everybody saw it, go back in the data, you can find out where it was picked up on radar and can actually help zero in on how to find the meteorites, so it was useful for that reason. So, and also the GOES-16 geostationary lightning mapper on the GOES-16 satellite picks up these things also, so lots of interesting ways to see these, but this is nice and friendly, and so we don't have to be concerned about it so much. And so this for a minute here, I'll play something that's a little more dramatic. I don't know if we have sound, it's just dramatic music, but if you remember in 2013, over Chelyabinsk, Russia, all the people with their dash cams, there was, it's coming out of my screen, there's some overly dramatic music there, but it's the boom, really. I'll turn it up a little later.
I love how he didn't even slow down.
Yeah.
It's Russian. Do its best. There's no sun out there.
It did.
We'll freak out over that.
And Chelyabinsk is like their equivalent of our Los Alamos. So can you imagine something like this happening and not knowing,
It did break a bunch of glass, didn't it?
It broke a bunch of glass windows because it detonated high in the atmosphere. Everybody saw it, but it took a while for the shock wave to come down to the surface, blew out windows, and thankfully nobody was killed, but there were a lot of injuries from the glass.
Wow.
How big was that one?
So, what was that?
How big was that?
It was estimated to be about 20 meters in size. Yeah. And if I don't have a slide on it, but if you heard of the Tunguska Impactor over Russia back in 1908, that was estimated to be about 40 meters in size. That was the area in Siberia where trees were flattened, yeah. And so this was about 20 meters in size. And of fireballs recorded by U.S. government sensors, that was the biggest one ever recorded. So that's it. That's it there on the map. The energy released from that. And more recently, kind of look over here. It's sort of hidden on the plot. This past December, and this is thought to be an unusual thing, maybe a once in a century type event. This past December, there was one not as large, it was like about a third of the size of Chelyabinsk, but still we didn't think we'd see something like that so often. And that was actually picked up. This was over the Bering Sea. And so unlike Chelyabinsk, where a lot of people saw it and experienced it and were injured by it, this was over the Bering Sea. And so it wasn't widely seen except by government sensors, and then the Terra satellite was actually able to image it, and that dark streak, that's actually not the fireball. The fireball's right here, and that's the shadow of it on the clouds. And so anyway, so these things happen, and so this is all great, and even Chelyabinsk would be nice to know about that ahead of time, because you tell people don't go near the windows. But what if it's something larger? So anyway, going into the functions of the office. So I don't know if anybody here was in the military and has heard of an OODA loop. And so, okay, I see some nodding there. Yeah, observe, orient, decide, act, and assess. Lindley Johnson, who is our planetary defense officer at NASA headquarters, actually came from U.S. Air Force Space Command before coming to NASA, and so he brings a lot of this with him. And our program kind of fits into that type of loop. And sorry if the text is small, but that observe, orient, decide, act, assess, and then lather, rinse, repeat, keep going around. The same sort of thing with near-Earth asteroids. You want to detect them, find them, follow them up so you can determine their orbits, characterize them. What are they made of? Plan if there's an issue, and coordinate with interagency and international partners. Mitigate, do something about it. Deflect the asteroid, emergency response, assess, start over again. And so NASA doesn't do it all, but the Planetary Defense Coordination Office is part of coordinating that and kind of providing a primary coordination node in the U.S. government for that purpose. And this is just showing all the different projects we're involved in and how they kind of fit into that. Not readable that way, sorry, but here it is kind of on our fancy rollout version. Again, the idea of searching, detecting, and tracking them. Characterizing, what are they like, coordinating and planning. Here we've got activities, here are some of our interagency efforts. Mitigating missions if you have to do something about it. Assess it, assess what happened, and keep going around. So let's start plowing in. First off, so how do we find them? And so I'm going to talk about NASA's Near-Earth Object Observations Program, which is what I manage, that part of the whole bigger structure, and our progress against objectives, which has been set for us by Congress, actually. So current survey systems, some of the major producers of discoveries, actually NASA-funded telescopes are providing about 98% of the initial discoveries, and other telescopes around the world provide the additional observations. The Catalina Sky Survey is a major survey out in Arizona by the University of Arizona with two telescopes and one follow-up telescope. The Pan-STARRS survey on Haleakala and Maui is the other big producer of discoveries. And Bruce, here we go, Atlas. He was asking about this earlier. This is another set of telescopes on Haleakala and Maui and on Mauna Loa on the Big Island of Hawaii. They're smaller telescopes that are developed to be very automated, robotic, to scan the skies, to scan the whole sky like in a couple of nights, and they're not as large, they won't go as faint as the other surveys, but to pick up maybe some asteroids on an impact trajectory that made it through the others. So to kind of fill in the cracks. So these are all very complementary. The other thing about Atlas, if you saw, like a month or so ago in the ARRL letter, or on the QRZ homepage, or even recently in our own newsletter, there's a story there about a young woman who discovered a comet, had a comet named after her. She's a ham radio operator, out on Oahu, and her name is Heather Flewelling, and her call is KH6. I can't remember the rest of it offhand. And she's actually the planetary defense researcher on the Atlas survey. So there's kind of that neat crossover there with radio. And the Air Force has the Space Surveillance Telescope, which they use for looking at artificial objects in orbit. But there's also asteroids also pass through that field of view. So MIT Lincoln Labs has a program on that telescope to pull the asteroid data off of it. But it was in New Mexico, and it's being moved to Australia right now. So once that comes back up and running, then that'll give good southern sky coverage. And finally, NEOWISE, this is the Wide Infrared Survey Explorer, which was an astrophysics mission. It wasn't an asteroid mission. It was surveying the whole sky, looking at objects outside of the solar system, but it was also good at picking up asteroids. And it worked in the infrared, which I'll explain later is good for getting information on sizes of the asteroids. It's kind of hard when you're just looking in the visible. And so it's kind of a repurposed space telescope. It was reactivated after it ran through its cryogens and only had a couple of channels left that didn't need cryogen. And it was reactivated, and so it's being used. It's making asteroid discoveries, but really its contribution is in the area of sizes. And so what NASA does actually fits into a larger worldwide effort that is a UN-recommended coalition of the willing. These are the signatories to the International Asteroid Warning Network, or we pronounce it IWAN. And there's a website, iwan.net, that's actually it's hosted at the University of Maryland for us. But it represents all of these, NASA and all of these other agencies and observatories, and even an amateur astronomer in the UK who have signed on to essentially bring their resources to bear on the issue. But there's many organizations and observatories outside of this group who are still heavily involved in the effort. The other big piece of the puzzle, you get all these data on asteroid positions. What are you going to do with it? The Minor Planet Center is the clearinghouse for information on small body positions, any of them, asteroids, comets, Kuiper Belt objects, all of that goes to the Minor Planet Center, those position measurements. And so they receive all of that. They're also responsible for identification, designation, discovery credit. And this is actually operating under NASA's Planetary Data System Small Bodies Node at University of Maryland. The Minor Planet Center itself is up at Harvard University, the Smithsonian Astrophysical Observatory, the Center for Near-Earth Object Studies. And so they take that information from the Minor Planet Center and they do orbit computation, precision orbit computation. They do that way out into the future to see, does anything pose an impact threat? We're going around the racetrack, the asteroids are going around the racetrack. Is there some point where there's going to be a collision? That's what they're looking for, to see if there's anything in the catalog that can cause a threat. And then also short term, even for objects, even when something is discovered and has yet to be confirmed by follow-up observations, they run it through the system and see if an alert should be sent. And if there is an impact, they would predict the time, location, and geometry. And so I'll cover that a little more later. So where are we? How many of these things have we found? This is by year. So again, NASA's program started around 1998, and all the different colors represent different surveys, and different surveys kind of reached the limits of their capabilities and then trailed off. And so what I mentioned earlier, the Catalina Sky Survey is there in green, and the Pan-STARRS is in pink, and Atlas is in peach up there. So these are the discoveries, and there were 1,836 discoveries in 2018. This year, 842 so far this year. The weather has been really, really bad in Hawaii. In fact, Haleakala got hit with a bad ice storm that took out the whole Air Force installation up there, the power. They're getting back online, we fell off in 2018, and maybe we'll see if we catch up more in 2019, but it's been a little rough weather-wise, and so that's one of the hazards when you do ground-based astronomy. You're subject to the weather. And so one of the things that Congress has tasked NASA with doing in particular, we try to find all the asteroids. This represents the 140 meters and larger. And so kind of a similar plot here. We've kind of rolled off again because of the weather. And so we'll see what happens.
How far off are those discoveries?
How far off? Oh, you mean where were they when they were discovered?
Yeah.
It all depends on the size and where it was in the orbit. I mean, you're not going to be able to find things if they are maybe too close to the sun or too far away, too faint. But we're talking about we start getting to magnitudes like 23, 24, 25. That you're not going to see those with these telescopes. But in terms of sizes, it just kind of depends on again how big they are. And I'm going to show something later about because also how. Are they small and bright, or are they large and dark? So anyway, I'll cover that in a minute. But for all the numbers, we're up to, just recently, we hit the 20,000 mark for all near-Earth asteroids. So this is over time. It's what's been discovered. And you can see here, the red represents 1 kilometer and larger objects. Those have kind of trailed off, thankfully, because they're larger, there's fewer of them, they're easier to find, and so only finding maybe like 4 or 5 a year. And these others are the smaller ones. These represent over 140 meters in size, up to 1 kilometer here, and then these are the rest of them. And so you see the rest of them, we just keep adding and adding. So we're not trailing off yet. Of the potentially hazardous asteroids, the ones that come awfully close to Earth's orbit, there's getting close to be 2,000 of those known, and 155 over a kilometer in size, and 107 near-Earth comets in the catalog too. And that doesn't include the ones that are like new discoveries that kind of come on through from the outer solar system. And NASA's search started in 1998, so that's where you can see things really ramped up. Okay, yeah, great, but what have we not found? And as we were talking about earlier, that's the concern. And so this plot actually got to replace this with a newer one. So you can actually model the population by based on what you're seeing in your telescope, your telescope's capabilities, people who do orbit modeling and population modeling can actually come up with an estimate. And so this red line represents how many of different size bins. These are all different size bins. Like here's like out at 10 kilometers, which was thought to be the size that took out the dinosaurs, for instance, down to like, here's a kilometer in size. And down here, George E. Brown survey limit, that represents the congressional directive to find the 140 meters and larger in size. So this area represents kind of what we're tasked with finding, although we want to find all of them, because here down at the smaller size, as I said, about 40 meters is Tunguska, and then here at Chelyabinsk, 20 meters. And this represents the devastation for these larger objects. The dinosaur won global, yeah, but as I said, regional with these 140 meters and larger, and even the smaller ones, city sizes, something like Tunguska or Chelyabinsk could still be devastating. And so these green bars represent how many in each of those size bins have been found. And so this yellow triangle kind of represents what we have to fill in. But look at this scale here. This isn't a linear scale. And if I were to plot this on a linear scale, it would really jump up there. And so this other plot kind of represents how we've done, and it's jagged, small number statistics. But here's maybe a better way to look at it. This is just the 140 meter and larger ones. That population is estimated to be 25,000 near-Earth asteroids. And as of January of this year, these are kind of broken into different size bins. The 1 kilometer and larger, pretty much found them. These are some other size bins here down to 140 meters in size. But the takeaway is these dotted regions, that's what we haven't found. And so we're just a little over the third of the way there. And in the congressional directive, which was given back in 2005, we're supposed to be up to 90% by next year. So we're not going to make it, and it's kind of a mix of, being asked to do something, but then also needing the capability. And so at the current rate with the current search systems, it's going to take more than 30 years to complete the survey. But we're looking at other technologies for doing this. So, and I'll bring that up in a minute. But okay, so we find them, great. Well, how do we learn more about the ones that have found? Because how do you know if one's going to be a problem if it were to hit us or not? There are some assets that are used for characterization, not to find them, but once you find them, to study them. The other telescopes for finding them have wide fields to search the skies, and you want telescopes with narrow fields to zero in on particular ones and have instrumentation to study them, to learn something about their composition. NASA's Infrared Telescope facility out on Mauna Kea in Hawaii is one of those facilities. When I got to actually do science, I used to use this telescope a lot, and now I'm responsible for keeping it going for other people to use science. But it's actually it does all kinds of science, planetary and astrophysics, but it's very good as an asteroid characterization asset. Planetary radars, where you bounce radar off an asteroid and the return tells you something about it. Goldstone in California and Arecibo in Puerto Rico are the two radars that are used. You can't use radar to search for asteroids. There's just not enough power, so it's not like at the airport where you can sweep around and search. Asteroids have to come close enough for interplanetary radar. You have to come close enough, and you have to know where they are so that you can bounce that beam off and bring it back. But if you can do that, you can really learn a lot about shape and other properties. And finally, the Spitzer Infrared Telescope. Oh, first of all, Bruce. Yeah.
Is the China fast dish part of this?
It doesn't have a radar on it. So the question is about the China. There's a large dish, kind of like Arecibo, and larger in China, but it doesn't have a radar capability on there. It's just a radio telescope. The other asset, the Spitzer Infrared Space Telescope, is also used for characterization, but it's reaching the end of its mission lifetime. In fact, this is its sunset year. At the end of the year, it's going to cease its operations. So, and then we won't have that capability. So, but what are the critical questions here? You need to know, if there's going to be an impact, you need to know when it can occur and how bad it would be, because otherwise how do you prepare? So the when comes from the finding them and determining the good orbits that I mentioned, and the how bad comes from measuring the energy, and the energy is the kinetic energy, 1/2 mass times velocity squared, and it's the velocity you get from measuring the orbit and measuring the motion, but you get the mass, or you get the sizes from or you get the mass from getting your size roughly, and that you just need diameters. And then on top of that, there are things like composition, porosity, multiplicity. Is it one or two of them? And how is it spinning? What is it shaped like? I'm not going to step all through this, but this just represents a bunch of the things that we ultimately want to know: size, mass, orbit, shape, so that something can be done. So going back to radar, the radar is a follow-up instrument. They have to be close, a tenth of an astronomical unit, or the 150 million kilometers, to be able to do this. And in fact, I put the wavelengths here because here we're finally getting to the radio for the club here. And so how does it work? So this little animation shows the radar signal is bounced off the asteroid, and then from the return, you get information on the shape, size, and how it's rotating. That round trip time tells you something, and there's some penetration into the surface, which gives you information, the scattering. So it gives you information on the properties. And so these images that you get, they're actually not true images. The idea is to take this and convert it into a true image or true shape model. But what you're seeing is the time delay and the Doppler frequency. So it's a little tricky looking at radar images, and I have a hard time getting my head around it, but you can still get a lot from it. So there's some interesting shapes. You find that some of them have moons. In fact, a decent percentage of asteroids are actually binaries. They have like little moons, or here's a trinary system, or sometimes they're even contact binaries, like this one, 2014 JO25, and lots of other interesting shapes. And again, these are the radar images, but that kind of translates into, that can be, it's difficult, but it can be turned into a true shape. And I mentioned earlier the WISE spacecraft that's been reactivated as NEOWISE, which is also getting toward the end of its mission because it's in a sun-synchronous orbit. It's precessing because it doesn't have maneuvering capability, and eventually it's going to start getting light down the tube, and it's going to heat up because it's an infrared telescope, and so it will lose its sensitivity. We thought that would happen last year, but as you know about the solar minimum, how that's affecting radio, well, it's also because the atmosphere hasn't, I guess, been expanding so much because we're at the solar minimum, there hasn't been as much drag on WISE, and so it's actually continuing to last longer. Take a spectrum in the lab, like this is olivine here. You could look at the shape of the spectrum in the lab, and then if you use a telescope and take a spectrum of an asteroid, you can say, oh, I see that same shape there. So maybe there's olivine in that asteroid. So there are ways, at least it doesn't, might not tell you exactly what the composition is, but you kind of narrow it down to what the composition might be by looking at the spectrum in the infrared and comparing it to what you see in the lab with different compounds and different meteorites. And again, the infrared telescope facility in Hawaii is one of the premier places to do that type of work. And then also, these things are spinning, and some spin slowly and some spin quickly. And so let me just step through here real quick. So here's a case. Can you find the asteroid there in Discovery images? If you stack them up and play them like a movie, yeah. So it's I'll go ahead for time and say, so here, there it is right there. You can kind of see it moving against the stars. And so that is how you find these things, because you see these fixed stars and these things moving across. Drives the astrophysicists nuts, but it's great for us. But they're also spinning, and you can tell that by looking at the light. That light might change over time, and so if you measure the light, like here's one from the asteroid 433 Eros, measuring just all the light that's coming, it's changing over time, and you can learn something about the rotated, so it can be kind of complicated in taking those light curves and backing out what the shape is. And so the light curve of Eros was different at different times, and so this was kind of the shape that was pulled out of that just from the light curve, something elongated. And then ultimately there was a spacecraft that was sent there, the Near Shoemaker spacecraft, and that's what the asteroid actually looked like. So it gets you in the ballpark at least with something like this. If you can get radar on it, then you can get a whole lot closer. But even with the light curves, you can get information on shape. Because again, like what you saw earlier, these things, even the big asteroids, they're still just a dot in the telescope, but you can still get information from them through some of these techniques. Okay, and finally, just the best thing is to send a spacecraft out there, and you may or may not have seen some of the results from some of the missions lately. The Osiris Rex spacecraft is out at the asteroid Bennu, and just an example, here's Bennu's orbit, and here's Earth's orbit. So this is an example of one of these potentially hazardous asteroids, and Bennu still doesn't have any significant chance of impacting Earth in these models that go way out, but still one to keep an eye on just because it is pretty close. But right now, it's just a cool science target. And the Osiris Rex mission is out there right now. Okay, here, thank goodness, because it's NASA, we have to have complicated acronyms, and I guess we keep running out of acronyms, so we have to make them even more and more complicated. It stands for Origins, Spectral Interpretation, Resource Identification, Security, Regolith, Explorer. So we have to make it complicated. It was launched in 2016, and it arrived at the end of 2018, and next year, it's been doing its reconnaissance. Next year, it's actually going to use the sample arm and take a sample, and it will return the sample in 2023. I know it seems like a long time, but again, you've got to get in the right position in the racetrack around the sun to be able to get back to the Earth and return that sample capsule. So it's one thing to get the meteorites off the ground. It's great. That's fantastic sample return. You can go pick them up, but you still don't know exactly where it came from, the context and everything. And so this is going to be ground truth. This is what this asteroid is made of, and be able to analyze it in the lab, some very primitive material. And so if you've seen some of the imagery online, it's been really fantastic. The radar shape models actually were very much like this. In fact, I meant to put that in here. And so when they actually got out there, sure enough, that's what it was like. And this is like a small rubble pile type asteroid and the spinning has caused that kind of muffin-shaped waste that it has there. And even the radar picked up this big boulder that's on there. And here's some close-up of the surface of one of the views, but it's just fascinating because we don't get to see asteroids like this normally. But that boulder, which this is the asteroid Bennu, and the team were very creative and called the boulder Ben Ben. So here's the boulder Ben Ben, which is probably the size of a couple Chelyabinsk, to give you some context there. So, and actually, somebody sent this to me, somebody put this online. If you see down here, there's Alan Bean and the Surveyor spacecraft from from one of the moon landings, just for context of the size, just of that boulder on Bennu. And Bennu is actually kind of a small asteroid. And you might have seen in parallel, the Japanese have the Hayabusa 2 spacecraft at the asteroid Ryuga, which is kind of a similar yet different rubble pile asteroid, and it's actually been really fantastic for coordinating science across the two, and the two teams are interacting a lot. Ryuga is about 900 meters in size, Bennu is about 500 meters in size, just for context. So this is the ultimate way, and if an asteroid was ever found to be on an impact trajectory with Earth, and you'd want to have a lot of lead time, so maybe you could send a mission like this out there to really characterize it well and study it so that you would understand if you were going to deflect it, which I'll talk about in a minute, how you would do it, because it kind of depends on how it's what its characteristics are. Okay, so there's the two missions. Okay, so what about the 2/3 of the larger asteroids that we still haven't found that I mentioned? So what do we do about those? Well, and so here's one of the issue kind of to the point about, here you got two asteroids the same size but two different colors, and in the visible from Earth they look very different. One of them's bright and one of them's dark, but if you could put on your infrared eyes, then they would look the same size. But again, in the visible, if you have these two objects of different albedos, different colors, one of them would be very hard to find in the visible, and that's what our surveys, our ground-based surveys, work in. But the infrared, you'd be able to see it, but you can't do that from the ground. I mentioned NASA's Infrared Telescope Facility. You can look at some infrared wavelengths from the ground between these windows in the atmosphere where the atmosphere doesn't absorb as much, but there's still a lot of the stuff you want to get at. Our atmosphere blocks it, the water in our atmosphere blocks it. If you could get above Earth's atmosphere and you can have a telescope in space, that's why the WISE spacecraft is being used right now. But it wasn't designed to do searches, and it wasn't designed to do this kind of work so much, and so it's contributing a lot. But the idea would be to do something that's actually made to do this, and this is how you could accelerate that survey. What I mentioned, it's going to take over 30 years to do this. This is how you could do it right, and you could go after those fainter asteroids. Bruce?
And we've talked about this before, but in support of that, because you can't see them and whatever, there's the occultation concept. There's some of us amateurs that you're not seeing the asteroid. What you're seeing is the stars that are getting blocked by the asteroid, so it's like this white thing moving across, and you don't see it, but you see it, kind of.
Exactly, that's one way of studying asteroids. And there are some folks who do search for objects that way. You wouldn't be able to get the high volume, but there are some folks, especially looking even for outer solar system objects, where you're looking at a star and you see that star blink out and come back, and it's because an asteroid passed in front of it. And it's a different talk, I don't have slides on it, but the New Horizons mission, that after it passed Pluto, was looking for a new target. Actually, just today, their science results were released in Science magazine. Ultima Thule was this Kuiper Belt object that was found further out, and there's a bunch of leftover junk on the edge of the solar system, and it was the occultation measurements, setting up telescopes around the globe, and knowing that this object was going to pass in front of a star, but not knowing exactly where, so they set up telescopes all over the place, and some of those telescopes picked up that blinking out as the object went in front of the star. And that gave information on the shape, actually. In fact, I was shocked that it did as good as it did. But if you want to get the high volume of discoveries and get the sizes so you even know, are we finding the ones that we're supposed to be finding? Because from the visible, you kind of have a lot of uncertainty on the sizes of what you're finding. And the infrared, you can narrow that down. The idea would be to do a space-based infrared survey telescope. And so there's one, the instrument of it is in development right now with the available funding. It's actually designed to do this, to meet that congressional direction, to go to find NEOs down to 140 meters in size. And it's at the right infrared wavelengths to kind of get past that uncertainty in the visible where you're not sure. You're seeing something that's large and dark, or small and lighter in color. And this, instead of being like an Earth's orbit, which is where the WISE telescope is right now, this would actually be out at Sun-Earth L1, Lagrange 1 point. These are stable points around Earth's orbit nearest orbit, stable points, kind of balanced gravitationally, where you could put a spacecraft and it kind of stays put there. And putting an asteroid search telescope out at L1 inside of the Earth here gets it away from the Earth, which also puts out a lot of infrared, and you don't want to overwhelm your telescope. And you can look at along Earth's orbit in both directions, and instead of searching the whole sky all the time and maybe missing a lot of the things that are where the higher density of asteroids are, you could search systematically in the regions where you expect them, and actually get closer to the sun, the direction of the sun here, than you can on Earth. The ground-based telescopes, they're looking out here at night, which is great, that you find a lot that way, but you miss a lot of area that you could be searching. And so that's one of the projects that's going on right now.
Kelly,
Yes.
what about James Webb? Was it able to be captured?
That's a good question about the James Webb Space Telescope, which is in development, and it would be the follow-on to Hubble, or hopefully work in concert with Hubble. It's not a wide field telescope, so it couldn't be used for search because it's very narrow field, so you have to know what you're looking at, what you want to point at. Because of its thermal situation, it's limited where it can point. It can also only point like it can't turn itself fully away from the sun or towards it. So if there's an asteroid of interest, let's say we find something that is a concern, and it's in the area that JWST can look, then absolutely you'd want to point that at it. And so it can't be used for search, but it'd be fantastic to characterize an asteroid if it's in the right place where JWST can point. So absolutely. So, okay, show me the system in action. So here is, I'm going to show something more fun in a second. Here's the flow chart, the idea that you're surveying it, you find asteroids, you report them, and you get a rough orbit. Is it a potentially hazardous asteroid, or is it a potential impactor? And if not, okay, routine processing, publish the results. Or if you need even more, you do even more orbit follow-up. Is it still an impactor? Maybe you figure out that, it actually wasn't. What happens a lot is lots of times our surveys pick up artificial satellites that aren't in the catalog properly, and it gets flagged as a potential impactor, and then all of a sudden you find out, it's an ArtSat, it's an artificial satellite, it's okay. And so this system is happening all the time, and thankfully it's usually not something that's going to hit. But if otherwise you'd want to get more information on it, radar, and then alerts. The Minor Planet Center and the Center for Near-Earth Object Studies would send alerts. So let me show an actual situation that happened last year. And this is only the third time ever that an asteroid was discovered prior to impact, small asteroid. So this asteroid was discovered, here's its orbit shown up here. It was designated 2018 LA. It was discovered on June 2nd of last year. And it was discovered by the Catalina Sky Survey in Arizona. And so there's some of the discovery images there, and the little purple circle are the discovery images. It's an asteroid less than 3 meters in size, so this wasn't a concern. It was discovered 8 hours prior to impacting Earth. And again, it wasn't a concern, so there was no need to raise the alarm, but it kind of gave a chance to exercise the system. So it was still treated like, okay, because it's cool, we get to watch this, so we don't have to worry about it. And additional observations from the Atlas telescopes in Hawaii proved to be important for nailing down the impact location. So what about 2018 LA? So the Minor Planet Center and JPL Center for Near-Earth Object Studies warned the Planetary Defense Coordination Office of potential impact. And the Center for Near-Earth Object Studies calculated the impact corridors with the data available. So initially, with just the data from the Catalina Sky Survey, you only had a few observations, and you're trying to calculate an orbit, and there's a lot of uncertainty on that. And so, but it was close, so you knew it was going to hit the Earth, but it wasn't clear if it was going to be in the Atlantic, Africa, over Indian Ocean. There was this wide region where that impact corridor could be. Oops, I'm sorry, is that me? Maybe I'm getting too close. Picking up other signals. Oh, the battery just died? Okay. Okay, I can use my mom voice. All right, so but after the other observations were included, look at this. The predicted impact region is shrunk down to an area over southern Africa. And sure enough, okay, well, first of all, so at the right time, a bolide was detected over Botswana at the right time, the right brightness, and again, more surveillance cameras. There was a farmer, I guess he was walking home one evening from his neighbor's house, and he saw this happen, so he goes back to his neighbor, and he says, why don't you go look at your surveillance camera? And this is what was seen, and so this was the impact. Now, it looks like it's hitting the ground. It's actually not. It's just it's over the horizon there, because this did break up in the atmosphere. It did not reach the ground intact. But still, again, just to predict it and then have this happen. And I showed that map earlier of fireballs detected by U.S. government sensors, and sure enough, this was detected, and so this is now in the catalog. 2018 LA was represented there, and that's where the impact happened. And all of this, by the way, is on this website for the cneos.jpl.nasa.gov. May have been mentioned in general, these position measurements, the close approaches, the long-term analysis of impact possibilities. It's all public data. So I say that because sometimes we get these television shows or movies where they say, oh, the government's going to cover it up. It's all out there public, plus you're not going to cover the sky, so it's all out there. And also Comprehensive Test Ban Treaty Organization infrasound sensors also detected the bolide. You're listening at frequencies below what we can hear, and for other purposes, they also detected it. So it was a neat test of the system, right on down to actually going out and hunting for the meteorites. It was in, I guess, a wildlife preserve, and hence the the rifle there. This is just one of the meteorites that were discovered after the fact. So this is a case where you had asteroid was discovered, impact was predicted, impact location calculated, impact actually measured, happens, go find the meteorites afterwards. This is only the third time it's happened, or one of the other times it was over water, and so there were no meteorites recovered. But it's happened 3 times. In fact, it's interesting, the same guy at the Catalina Sky Survey was responsible for all those discoveries, and so I keep saying, somebody's got to fire that guy so this stops happening. And so what are other things we can do? So that was kind of a real life exercise. We actually, that just happened. We actually did an intentional exercise in 2017 to say, okay, we knew of an asteroid that was going to be coming back on a close approach by Earth. It had been discovered earlier. In fact, there was press about, will it hit? It was discovered in 2012. Is it going to hit Earth in October 2017? Well, there were enough observations to get a precise enough orbit to know that it wasn't going to hit Earth. So that was known for sure, but it still wasn't known exactly how close the close approach would be. So it was kind of a chance to say, okay, we know this isn't a problem, but let's get the community together and let's plan a campaign around trying to recover this thing as it becomes visible again, as it comes close enough again. Let's try to find it, find out what we can about it, treat it like it's an impactor, and exercise the whole system, even to the point of notifications that are done at NASA up through the agency and to the White House and the rest of the government. Yeah.
Aside from telling people to stay away from the windows, what would you tell the public to do or something like this?
Well, the ideal thing would be to find something like this years or decades in advance and not have these short warning situations. But yeah, we'd warn other government agencies, or if it's something, an impact that's going to take place in another country, then through the State Department would handle that, and you just give all the information, and then emergency response planners can handle it that way. But the ideal thing is that you have a lot of notice, so you wouldn't have this quick scramble. So, but we did treat it as this is an actual exercise, and I have very fun charts here. But the close approach was October 12th of 2017. And we had lots of facilities involved. There were a number of countries involved, and signatories to the International Asteroid Warning Network and others. We had 14 countries involved, ground and space-based assets. And so here's a picture of the recovery. Those are star trails where the telescope is tracking the asteroid, and the asteroid's moving against the stars. So unlike those other images where the stars were fixed, here the stars are spread out because it's following the asteroid. But that was the recovery image. And then observations continue to be made. And so here's an animation of the close approach of that asteroid, and you can see all the geosats and the other satellites. How fortunately space is big. There was a close approach that in the animation it showed it went pretty close to a DirecTV satellite. I thought, you know what, I tell you, if we took out DirecTV, then people would say, okay, we got to do something about this asteroid. I took out my DirecTV. But actually, when an asteroid does have a close approach within the distance of the geosynchronous satellites, there's a notification that's sent to the Air Force about that. So anyway, so that was that asteroid, and we had all this participation. It was tracked. There were radar observations that showed it to be oblong, light curve. Properties were measured so that could go into some modeling. It could be sort of a practice run for if it was an impactor, trying to calculate what would the damage be. We went through this notification process to the White House, other government agencies. The interesting thing is before the campaign, the possible impact solutions showed a probability of 5 in a million that it would impact, and that's why there wasn't any concern about it impacting. As the new observations were made, all of a sudden it looked like there could be an impactor. It got up to 1 in 180 chances, and when we get to 1 in 100, 1%, that's when we'd start raising the alarm, the 1% level. And it never got to that, but then eventually by the end of it, as you got more observations, all impact solutions were ruled out. And that's because if you think about it, you have this uncertainty. Think about like hurricanes, when you watch on the news there and they show that cone of uncertainty as the hurricane is approaching land, and it could be anywhere in there. That's kind of with the asteroid too, where it could be anywhere here or in the future there. And so the Earth is in there, and then as you get more observations, that uncertainty goes down, and if the Earth is still in there, then the probability goes up, but then eventually that uncertainty goes down to the point where the Earth is outside of it, and then it goes away. And so this could happen a lot where something is discovered, and all of a sudden the probability goes up, and then as more observations are made, better data, all of a sudden it's not even a problem. And so that happened here. Right now, we have another campaign going on. It's a little different. It's a characterization campaign. It's a binary asteroid, 1999 KW4. And the International Asteroid Warning Network, at their last meeting in Vienna, decided to do this as a campaign. It's a binary asteroid. It's a chance to see, like, okay, what characterization data can we get together in a short period of time? And it's sort of a practice for the DART mission, which I'm going to talk about in a little bit, which is to a binary asteroid. So you may or may not see something about that in the news. It's not coming nearly as close, 38.5 lunar distances, but it's within radar distance. And so it's really more to see how can we learn about the properties of an asteroid as opposed to treating something as a potential impactor that's going to come close. Okay, so finally, here's some of the cool movie stuff. How would we deflect an asteroid to keep it from impacting Earth? So you might see a lot of techniques out there, but there's a couple that are really the most mature technologically. And this sort of represents the whole space of warning time. You know, if you had, the more time you had, or the larger the asteroid. You know, if you really don't have a lot of time, or it's a large asteroid, you'd be up in the nuclear realm. But if you have more time, or if it's not as large of an asteroid, kinetic impactor, that's the most mature technique. You smash something into it. All you have to do is change the speed a little bit way ahead of time, and then it would miss the Earth in the future. And so, and doing that with a kinetic impactor, that's the most mature technique technologically, just hitting something. Another is called the gravity tractor, which involves essentially using spacecraft mass to kind of slowly tug the asteroid off its course a little bit. Oops. And okay, I guess that's all I had. And then we talked about nuclear up there. So let me move on. So DART, this is actually a real thing, the Double Asteroid Redirection Test. This is going to be a planetary defense demonstration mission. It's in development right now, and it will launch in 2021, and it's going to impact the moon of the asteroid Didymos. It's a binary asteroid, it's a Didymos B. It's about 160 meters in size, kind of the size of that lower limit of the ones that we're really concerned about. And the idea is to change the period of the orbit of that moonlet around Didymos A. because that's actually something that's easier to observe than like trying to deflect an asteroid in its orbit around the sun. And so, we're not changing the orbit around the sun. It's not going to put it in a position where it's going to be a problem for Earth, because that's something people ask. And the observation is going to take place from the Earth, because this is going to pass close enough to make those observations when DART hits Didymos B, to be able to determine, okay, how much did we change the period of that orbit, and what does that tell us for our capabilities to actually do a mission like this in the future. And the Italians are considering sending a small CubeSat along, which would be great to have some observations there as it's happening. So we'll see if that all works out. And so here's an animation of DART on the plunge in there as it's going around Didymos B. And that impact, you see that plume material coming out. That's one thing we want to study too, because there's the momentum that's transferred by the impact that gives it that oomph, but then also that plume material coming off to give it that little extra push. Just like if I was standing on a skateboard and I threw a ball, I would slide back the other way. Well, that's kind of what would happen with that plume. And so that enhancement factor is something that we want to measure too. So it's going to be very interesting when this happens, and this is in development right now. In fact, there was an announcement recently. The launch vehicle was chosen, and it's going to go up on a SpaceX Falcon 9, so that should be kind of fun too. So another technique that I mentioned, the gravity tractor, and it's, again, not like a science fiction term, and it's not using special waves or anything. It's just using the mass of a spacecraft, or the idea of an enhanced gravity tractor would be, say you had a spacecraft, there was a mission concept to do this, spacecraft that could actually go to the asteroid and grab a boulder, like you saw Ben, all kinds of boulders, get a little more mass, and then just hover there. If you had years of advanced warning, then you have a lot of control here. You just hover there, use that mutual gravity just to tug it just slightly, and then you can back off and come back in. So you have a lot of control with a gravity tractor, but you need a lot of time to make that work.
Doesn't that require also that you have a fairly powerful spacecraft to move a large mass off the surface? And then
Yeah, you can only lift so large of a boulder because, yeah, you're right, and mass, just getting mass off the Earth is hard, so you're finding that balance of how much mass could you put on the spacecraft and actually get it out to the asteroid.
Question, I know last time we had the impact. But it was impacted the same, opposing directions. Would that have a slightly, was the same direction, slightly not at all?
Well, actually, it kind of, with all of these in actual impact situation, it would depend on the orbit and how we could get a spacecraft out there, because putting something in the way of an asteroid is a lot easier than trying to get it around in such a way that it could come up behind it, but it just kind of depends also on the direction you deflect it. But in the case of DART, it's going to be impacting in such a way to slow it down a little bit as opposed to speeding it up. And so yeah, that impulse there is actually going to slow the orbital period a little bit.
Which
So
then
good
in
question.
turn slows the primary.
Well, yeah, and it won't be significant enough to really, but yeah, you're right, in the conservation of things, yeah, but it won't be that significant for that. So moving on to the fun one. Oh, I got my title off center, I apologize. So it's not like, a lot of the movies, yeah, maybe at the last minute you would disrupt it if you really had to, but if you disrupt it, then you have all this stuff running down. And you still would like to have years' notice if you go out and do this, but the more effective way, instead of just going up there and disrupting it, would be to detonate next to the asteroid, and then the surface, asteroid surface, would be irradiated by the blast, and that irradiated shell would blow off in one direction. Sorry, expensive animation, so that's all I have right now. And so the reaction direction would be in the other direction. And that's really how you'd want to use something like that, and not so much going up there and, a whole Armageddon type situation and blowing it up.
All
So,
those pieces are still coming.
all those pieces are still coming at you, yeah. And so some might hit the Earth, but yeah, this would be the preferred way to do this. And this we can't do a demonstration like we can do with DART, but NASA coordinates with some of the national laboratories where they've got the expertise to do modeling to have some idea of how this might work. So those three areas are kind of the most mature areas should we have to do something, but you'd want lots of notice. And so trying to wind down here. So there's a plan, right? What's the plan? Do we have a plan? And so we actually have, it's really more the plan for the plan. I mean, what I've showed you so far, it's underway right now. We're doing this, but let's say there's something that is an impactor. We don't want this to be the first time anybody's heard of this. And NASA and FEMA have actually been coordinating for quite a while on tabletop exercises, looking at possibilities. It's just, and again, they've got things they need to worry more about hurricanes and tornadoes and everything, earthquakes. But again, it would be nice if something does become a problem that this isn't the first time they've ever heard about it. But now there's an interagency plan for the plan, the National Near Earth Object Preparedness Strategy and Action Plan that was released last June. And it involves, it's an interagency working group of all these different agencies with different responsibilities, co-chaired by NASA and by the Office of Science and Technology Policy, but with a bunch of other organizations here. Anybody here from any of these organizations? Okay, yes, some of them are represented here, so this may be news to you, but it's at different levels of visibility in different organizations because, again, we're kind of just getting started, but what some different responsibilities would be. And so the goals in this action plan: enhance NEO detection, characterization, and tracking capabilities, improve the modeling, predictions, and information integration, develop technologies for NEO deflection and disruption, increase international cooperation on notice, for detection, and then emergency responses outright of them. In fact, who all here is part of the Amateur Radio Emergency Service? Who's part of ARES? Okay, we've got this is fantastic, a number of folks there. We had the International Planetary Defense Conference just a couple of weeks ago in College Park. It's only every 2 years, and it hasn't been in the U.S. in 6 years, but it was local here just a couple of weeks ago. And Mr. Damon Penn, who's the Assistant Administrator for Emergency Response at FEMA, gave one of our lunchtime keynotes. And so smart aleck I am, I got up there during the question time and identified myself. I said, Kelly Fass, NASA headquarters. My call sign is November 3 X-ray uniform Juliet. I said, I'm going to be speaking to my Amateur Radio Club that I'm in, and many of them are members of the Amateur Radio Emergency Service. Can you comment on the importance of communications and for groups like ARES and amateur radio operators being involved? And so it was nice to hear him kind of validate that and recognize the importance of ham radio operators in that event, because earlier in his keynote address he'd even talked about how there are times where the public just need to step up and help with things. He talked about situations like these where folks are stranded in a snowstorm on the freeway and people are taking them in and all that, and so that's why this came to mind. And so just wanted to make sure that was highlighted, and I was very pleased with his response, because even afterwards he thanked me for the question, and so I did that. And I'm not a member of ARES, and one of these days I should be, but certainly getting into this side of getting into planetary defense, which is different from what I did in my earlier life at NASA, kind of maybe circle back around and appreciate amateur radio all the more just because of this coordination that we're doing with FEMA and with other agencies. The goal would be to not let it, NASA needs to, and others need to do their part to try to keep it all to the left of boom, but at least understanding if it gets to the point where it's to the right of boom, trying to give the best information possible so that the planning can be done on that side, and folks like those in ARES and others know what they're dealing with. So I'm sorry this is going on so long, but I want to cover exercise real quick. So I don't have slides on. We've actually done these tabletop exercises, these impact scenarios. We actually had one 2 weeks ago at the Planetary Defense Conference where we took out New York City. But I didn't have slides on it. And this is from an exercise we did with FEMA in 2016. And sorry, it's kind of so word dense here. I'll move on. But the idea was that an asteroid is detected 4 years prior to possible impact. And the object is initially assessed to be between 100 and 300 meters. Again, that uncertainty, you see it in the visible and you know it's probably this size range, but you don't have that precision. And 1% probability of impact. Again, that's kind of the threshold we've set here in the US and also internationally, that, okay, that's when we start raising the alarm. But then as more observations come in, and the scenario rises to 2% after a week, and then finally after 3 months of observation, and we're starting to lose the object as we're, again, going around the beltway, and the asteroid's going around the beltway, and it gets out of observational range, by that point it's up to 65% probability of impact. And a little more information that's like 100 to 250 meters in size. And now we've lost it for a while because we can't see it. And so what do you do with that uncertainty? Get some characterization information. It's probably stony with some metal content. So, if something's again, the density matters. If it's kind of a fluffy object like we saw with Bennu, it might be different from than if it's some like solid, more metallic object. So by a year later, it is reacquired in the scenario, and now we're up to 100%. Okay, it's going to hit. And this impact region is 500 miles long and 150 miles wide, and so you've got something like this. So, yeah, how do you plan for that? But I mean, that's the thing. It's interesting, like working with FEMA, because Leviticus Lewis, who's our direct contact there at FEMA, who we work with, he's like, I just want to know where and when it's going to happen. And I understand that. Who wants to deal with these uncertainties? But the whole point is then get better observations to bring these uncertainties down, like I showed you with 2018 LA last year. And that red line is actually a series of dots. They do a bunch of different models, a bunch of different Monte Carlo models, they call them, a bunch of different possibilities based on the uncertainties. And that's what you get, this whole swath that goes over the Earth. And so as the scenario progressed, this tabletop scenario, as you got closer in time there, about 3 years prior to impact, now it's kind of compressed down to, this was a scenario we did out in California, so you got to be nice to your guests. You take out California. I'm actually from Hollywood. I'm also from Hollywood, California, so I figure, okay, I can take the hit in this way here, so I could be responsible for taking out my home state. And so, yeah, these dots all represent possible impact locations. It only happened in one place. It's not a strafing run here. It's just, we just don't know which one of those spots it's going to be. And so as this exercise progressed, we had folks who did modeling of what could happen should it hit in certain spots. What would happen if it hit way out of the city? What would happen if it came in over the ocean? One of the things, and what would the damage levels be? And I told Sergio I'm going to bring his his area of expertise into my area of expertise here, where we've got some impact cases if it's over the ocean, which is what Sergio works with. And so what would happen? It turns out, actually, folks have done a lot of modeling with asteroid impacts out in the ocean, and it sets up a different kind of wave than like if you had like an earthquake where the seafloor drops. This plot, it's possible that something way out in the ocean might not be as much of a tsunami hazard as we worry about, unless it's like one of the really big ones, and yeah, you got the movie situations. but let's say you drop something right off the coast now, and folks are doing modeling of this. What would be, now you don't have time for something to dissipate before it hits land, and so you could get a tsunami, or it could hit on land there. So anyway, getting close to the end of the exercise, this was more 6 months before impact, and additional observations now in the scenario, a flyby mission, so kind of like Osiris Rex spacecraft, but it's hard just to get something out and slow down to an asteroid. The idea was to get something out there quickly, and so it's a flyby, measure it, but then all of a sudden you've got a lot better information on its location, which helps you determine where it could possibly impact, and its size and composition, so you narrow that down a little more. So now we're down to like between 100 and 120 meters in size in the exercise, and we're really starting to zero in on the LA area here. So that's 6 months prior to impact, and then finally, 3 weeks before impact, getting radar on it, it narrows it down to the Rose Bowl. So I mean, so you gotta have some kind of a little fun with it, not take it too seriously, but this model here shows these color bands show wind speeds, and so here is like greater than 200 mile per hour winds from this impact, and this is like the not survivable region here, and then getting out to regions of less devastation. And in the scenario for our FEMA FEMA planners, there were folks who looked at the effect of the infrastructure there in the LA area, what that could potentially be. Maybe just for an exercise, just a tabletop, but again, being able to look at this now so that if it ever does become an issue, and hopefully we never even let it get to that point, but just to understand what could possibly be happening. So, and plus we're also learning at NASA and the science community how to better communicate with our other agency colleagues, because we're a bunch of nerds and we love to get down in the weeds and talk about uncertainties and everything. And how can we boil it down to information that's really useful that emergency planners can use in trying to plan for something like this? So hopefully it never even comes to this. So, but this could be the basis for emergency management decisions, and we want to improve the response planning, especially if there's limited time. So we're learning. So here we are right now wrapping up. In 1999, this is what was known about the near-Earth asteroid population. In 2009, here's what was known about near-Earth asteroids. And then here we are in 2018, this was the near-Earth asteroid population that was known. And then here's all the asteroids. So there's the asteroid belt out there, and a lot of those we don't worry about. It's those blue ones that make their way into Earth's neighborhood. We want to keep an eye on them. Again, a lot of them never even come close to Earth or Earth's orbit, but we still want to find them before they find us, so that if we have to, we can get them before they get us. And so if you've ever been out to Meteor Crater in Arizona, don't let this happen in your backyard. And so that's why we have the Planetary Defense Coordination Office. And that is too much of the fire hose, and so I'll wrap it up there and take questions.
Two questions.
Yeah.
Shoemaker-Levy knowledge hit Jupiter.
Yes. I should
How
have
much,
that.
knowledge did you guys get from that actual comet hitting a planet?
Well, it's interesting you mention that, because this summer is the 25th anniversary of the Shoemaker-Levy 9 impacts, and I'm actually pushing for NASA to do a couple of features on the anniversary involvement. The infrared telescope facility that I showed there, my first observing run ever was actually at that telescope for Shoemaker-Levy 9 impacts, and so that part of my government shutdown project was converting some video from 1994 into something that could be used. So anyway, I want to recognize that, because it was super important for comet science and for Jupiter science. I was actually doing Jupiter science back then, because it was a great chance to study what happens to Jupiter's atmosphere and how it settles back down. But it was kind of a big wake-up call, too, about impacts, that this is the first time it was discovered a year before impacts. So there was all this chance to plan a campaign to watch it and everything. But it showed that impacts are still happening. It's not something that just happened. We see the scars, Meteor Crater in Arizona and all that. It showed that they're still happening today. And thankfully, Jupiter, it's large. It's kind of most of them, other than the sun, most of the rest of the mass of the solar system is in Jupiter. Jupiter has a lot of effect on the orbits of small bodies, and so it's more likely to get hit by something than us. It's like the vacuum cleaner of the solar system. It also flings things at us too. So all of that kind of worked out together to make a fantastic science opportunity, but to also point to the possibility of impacts. And as I said, their NASA's program started in 1998, so just a few years after that. A lot of that kind of helped push things along to say, we need to pay more attention to our own neighborhood. And our NASA's Planetary Defense Officer was at the Air Force at the time and kind of working on this sort of thing. As he said, it kind of put the exclamation point on his thesis topic there that he was working. So that was a big player in again, kind of that reminder, just like Chelyabinsk was when Chelyabinsk happened, that actually the UN Committee on Peaceful Uses of Outer Space, they were having meetings there of establishing the International Asteroid Warning Network, and this other group, the same Space Mission Planning Advisory Group, which would address this issue. And then Chelyabinsk happened right when they were all there gathered in Vienna. So those things like that, Shoemaker-Levy 9 and Chelyabinsk, they've sort of been exclamation points, as a colleague calls them, on developing planetary defense over time. So,
yeah. Is when we talk about things impacting near us, have they looked into the possibility of much larger objects, say in the 140 meter range, hitting the moon and then impacting us afterwards, or is that just sort of like a tangent that someone else goes on?
Well, fortunately, space is really big, and so that kind of billiard ball effect, the odds are kind of slim. But all of the objects, I mentioned out at JPL where they track the orbits into the future and looking for close approaches and impacts of Earth. They actually do that for all of the bodies in the solar system. So it's going to be close approach or impact of the moon or Mars or other planets. So all of that's tracked, and or each other. But again, it is so big that the likelihood is low. And just in general, all of this, it's like a low likelihood of event, but possibly high consequence. So again, it is a possibility. I guess if you had something really huge, if it was enough to launch something out of moons, it could actually escape velocity off the moon and happen to come in the right direction. But fortunately, there's just a lot of space out there, so it would be even lower probability. But that sort of thing is tracked also. Is the moon going to be hit by something? So we even had a situation a few years back. There was a comet that was discovered, and on its way to the inner solar system, and it ended up passing close to Mars, and it wasn't going to hit Mars, and that could have been a fun science topic because nobody would have gotten hurt. And so but still, we have orbiters at Mars, and at the time I was working with the MAVEN mission. Goddard there, Sergio knows that it was going to be heading out to Mars, and this comet was going to come by with all this material around it, and that could have provided that could have been a hazard to the spacecraft. And so we had folks doing hazard studies to see what should be done, and they actually changed the orbits of the spacecraft so they were kind of on the other side of Mars as the comet with all its dust came by there. And there were actually observations of the upper atmosphere showing like the effects of dust on it and everything. And so yeah, looking for those collisions all over the solar system. Unfortunately, that's even lower likelihood than just getting hit, but you never know, so it's a good question.
I was wondering, certain times of the year, do you guys have like more overtime, like say through our passes through the Tard meteor shower stream, stuff like that? I saw your picture and it had all I kind of expected more paths as opposed to just kind of, it looked like just dots everywhere in a sphere. like there was no definition, you know what I mean?
No, you mean like the animation I showed at the end there?
Well, I know certain, yes, the animation that you saw, like, I know certain impacts have been connected with, especially explosive impacts have been connected with certain meteor streams.
Oh, yeah, well, actually most of the meteor streams, it's because it's the trail, the material left over from a comet as it goes by. And there have actually been some asteroid collisions or asteroid breakups, but it is pretty rare because even with this, if the dots were shown at the sizes they actually were, you wouldn't see it on the screen. So it looks a whole lot more crowded than it is. But like you were saying about certain times of year, that's a good question. Because most of that does tend to be just dust. Sometimes you get bright fireballs, but again, nothing of the size that we'd be concerned about, really making it to the ground and doing damage. So the annual meteor showers aren't really a concern. There's some who speculate about, are there any large chunks, in some of those, but not as much of a concern as just the asteroids themselves. But that's a good point.
Cool.
Let's see. You were talking about the wide field of view telescopes looking for, and if I remember correctly, a couple comets were discovered. Shoemaker-Levy was by people with telescopes in their backyard. Has the science advanced far enough with these new cameras that that's not likely to ever happen? I think it was late 90s when the Shoemaker-Levy.
Yeah, it was discovered in '93. Yeah, and that was actually Eugene and Carolyn Shoemaker and David Levy using a telescope at Palomar and searching a smaller telescope and surveying, and they were actually using photographic plates. And so it was kind of on just as we were changing over. So yeah, it wasn't quite so, but still, that was a different time, and it was kind of almost getting to the time when that things were changing, where you're getting CCDs and everything. And so yeah, that's a good question, because even as you go back here, like just showing of our larger surveys.
I would
Here we
think
go.
if you have a good sky map, and you probably have a much better sky map, then it would be easier for a computer to find things like that.
It is a lot harder now for smaller telescopes to make discoveries, and even here, you see this was an earlier survey that it kind of hit the limits of its capabilities, and then it was finding less and less and less because it could only see so deep. And then you have the competition now from these other surveys. They're going to find them first, and there are amateurs who still find them, especially comet discoveries, and you still. But there's a lot of comets now that are discovered by, like, there's lots of comet pan-stars and comet atlases, and so it is harder now to make the discoveries because these are finding them. It's harder with a smaller telescope to do it. There are folks who do follow-up observations once the discoveries are made, or even before they're confirmed. They go up on the Minor Planet Center website, and other astronomers can look there and say, okay, I'm going to go after that one. They can go follow it up and get additional measurements, and that's a way that amateurs have contributed. But again, it's still hard because the brighter ones, the low-hanging fruit, has kind of already been found, and it's the harder ones that are more difficult to find. But still, we have in my program, there's I hate calling him an amateur astronomer because his equipment is so advanced, but Robert Holmes, who's got telescopes in Illinois there, and he's just very good at what he does, and he can go to pretty faint asteroids and do this follow-up, get more observations. But again, it's follow-up. It is a lot harder to compete for discovery now, and so we really do need like the larger surveys because a lot of the low-hanging fruit has been found, and you've got these capabilities that are already there. But there are other areas where amateurs really contribute, like what Bruce is talking about with the occultation measurements. You're taking small telescopes all over, and they can't see the asteroid, but they can see the star when the asteroid passes in front. Or also monitoring the outer planets, like Juno's a spacecraft at Jupiter right now, but the amateur astronomers can do that continuous monitoring of the whole disk of Jupiter, and they've got some really nice equipment now, and so there are areas that amateurs can contribute. It's just that in finding them, it's getting tougher and tougher for them to convince. So, Bruce.
So I was just going to follow up on the question he asked and whatever, but yes, because that's my hobby besides radio.
Yeah.
And yeah, it's more follow-up. It's not so much discovery, but the whole optical, the visual occultation. You know the predicted paths of these things, and it'll blink a star. The problem with that is if you look at the shadow paths across the Earth where you're going to see it blink out, these things can be 10, 15 miles maybe wider depending on how far the asteroid is from the star. So they're very narrow, and amateurs will go out and will actually set up a fence a couple of miles apart, a dozen telescopes. But the point being is, in case there's some deviation from the path, but the point being is, if you're not within that shadow path, it doesn't matter how sophisticated your observatory, government-owned or whatever is, it won't see that blink out. And that's where the amateurs have an opportunity to contribute very significantly. We've done that over the years. But again, it's not a discovery thing. You've got to kind of know it's there. But some of those observations have led to some very remarkable predictions of the shape of the asteroid because of that star blinking out in there. So anybody that says, well, there's no room for amateurs anymore, there actually is, because you're portable and the big observatories aren't.
And in the right areas, there can be that contribution. And as you said, which telescopes see the blinking, which don't, tells you something about the shape if you have a whole distribution of telescopes. And in our scenario 2 weeks ago, before we took out New York City, one of the suggestions for how can we get some rapid information on this object that was in our scenario, and one of our astronomers suggested a big occultation campaign and to put money toward getting a bunch of telescopes and precise GPS clocks and everything, and do a good occultation campaign. So yeah, there are areas where there could be contribution. So, and I know I've gone over, and I'm happy to answer more questions, but I can let folks go too because I know it's late. But I really, really appreciate your time and hope you enjoyed it. And there's brochures and stickers and a few things back there that you're welcome to. And I'm happy to answer other questions, but I'm happy to let you go. But thank you so much.